Thank you. So, in the last lecture, so it's becoming more and more difficult, right, to give lectures here because the talks are better and better. So, yeah, it's becoming difficult to compete. So, right. So what I want to see now, so last lecture, so this will be the tutorial. Before I start with the actual things, let me mention two things that, so Prim kindly approached me after the previous lecture. He reminded me that, in fact, the open reversal between the Q and is between the Q and the QC isomorphisms of graphs. The other ones, between Q and QC, for example, they are settled using, again, the same machinery, as the same idea of machinery that I explained, translating linear binary constraint system games into graphs, attaching a graph to such a system. And the other thing is, there was, so Robin mentioned how about open problems. So what I decided to do, I will compile a list of problems with short explanation to each one of them. Instead of presenting this here, I think this is what I will do, and at some point I will post it on the workshops portal. Yeah. So in the last lecture, I mentioned how one can kind of have a candidate of a quantum graph, and we said, okay, this will be a certain operator system living in some dimensions here, right? So this is just an operator system, finitely acting operator system. And then we discussed games on classical graphs, and the natural question is, can we formalize this? Can we lift this to the quantum setting? Can we formulate a game on quantum graphs? And yes, we can, indeed. Somebody once said, famously. So how is this done? Well, we need to have some version of strategies of correlations in that case. So let me first look at the correlations, quantum versions of no-signaling correlations. So the starting point here is the following. You view classical no-signaling correlation as, this is, I fixed these sets. I view this as an information channel, classical information channel. According to my notation, this will be a certain channel. Let's call it gamma sub p, depends on p. So p is the whole family of these conditional probability distributions. This will be a map, trace preserving and positive, say completely positive, but it's the same here, from the tensor product of the inputs. Remember, these are the diagonal matrix algebras over x and over y to the tensor product of the corresponding outputs. Now, these are just the coefficients, right? When you analyze it with respect to a basis here, right? So that's a classical information channel. That has, in addition, of course, the no signaling conditions. So the natural thing to do here is, and that was done by Duan Winter, not remember precisely the year, maybe 2017 or something like that. So just replace these by matrix algebras, full matrix algebras, and consider quantum channels instead. So this would be gamma from full matrix algebra, this was my notation for that, tensored with my into MA tensored with MB. So this is a quantum channel. Which is also no signaling. It satisfies natural no signaling conditions. I will not try them precisely, but this means that if you want to define a map from MX to MA alone, it is well defined. And similarly, you can well define a map from MY to MB, which will be a quantum channel, like the marginal quantum channels exist. So no signaling as well. So this is the natural translation. Maybe what I can say, that's useful actually. It's an easier way to formulate it, just look at the dual, right? If you take a look at the dual, that's a unital completely positive map. The domains and the codomains are reversed. And the no signaling condition is simply saying that if I take the A system alone, embed it into the composite system, this will be preserved, this will be mapped to the X system alone. And similarly on the other side.
This is what you define as marginals of these maps.
Right, you can, if you have this condition, you can define obviously the marginal gamma star of the dual from X to A, and then you can take the pre-dual, that will be the marginal quantum channel now. Yeah. All right, so then the question is, so this will be the general no signaling class, QNS class of correlations, quantum no signaling correlations, as defined, as I said, by Guan and Winter. So the question is now, what are the corresponding classes, subclasses of those? How can one calibrate between different types? And the local type, let me denote it then like that. So the whole class will be Q and S. So the local type is probably the easiest to quantize. That will be just convex combinations of elementary channels, exactly in the way it was in the classical case. I will have a channel, this will be a channel from X to A, quantum channel. I will have another one here from Y to B, and I take all possible elementary tensor products, take the convex hull of those. What about the other classes? So to define the other classes, let's return to the case, to the classical case, and see what's happening there. So remember there, what I have is this is on. Let's concentrate on the QC class. You have a certain family of POVMs, one for every input for Alice. This family gives rise to a map B from the diagonal algebra of over A to the diagonal algebra of X tensored with the corresponding B of H, where these live on H, these operators live on H. In the way that, of course, if you have just elementary matrix unit here, matrix unit in the diagonal, you will map this into a diagonal now operator, block operator matrix as diagonal, which will be composed by the corresponding EXAs over X. That's a unital, completely positive map by the property that this is a family of POVMs. Similarly, we'll have for Bob here, YB, right? You will have a map C from the diagonal of B to the diagonal of Y tensored with the same B of H, the coefficient space. And using this, you can kind of take the dot product of them. They have commuting ranges, so you'll have a nice positive, a completely positive map. So let's quantize this. Just I replace just the diagonal matrices, matrix algebras by full matrix algebras. So I will consider then phi now will be from the full matrix algebra of A to the full matrix algebra of X with coefficients. Similarly, Psi will be some UCP, so this is UCP. Similarly, I will have a UCP map from on the Bob side, UCP, with commuting ranges in the sense that the corresponding operator coefficients arising from these two maps mutually commute. Let me write that as commuting. Commuting on the B of H leg. All right, so once I have these two, now imagine the case where this is just one-dimensional. If I do the procedure that I will do, I will arrive just at the elementary tensor phi tensor Psi. If not, what I will do is, so I need to arrive at a map gamma from MXY to MAB. There is only one really way to do that now. If I have a certain state, rho, and I want to pair it with a certain operator T upstairs here, so this has to be a state, I need to pair it with an observable. This will be the same thing. By definition, this is the definition of gamma. I will have to pair rho with so I will have here phi, the product, the operator product of these two. it will have to be applied at t. I will have operator coefficients, so I need to slice it, so therefore that's the convenience of writing lecture notes in iPad in class, so you can just shift everything as you wish. I will need to slice it down with a certain state on B of h. This will need to be paired with phi dot c applied to t. If I want to write it in a coordinate form, so here rho is the variable, omega is a certain state on B of h. Let me write it in coordinate form, which I will need afterwards. So in coordinate form, it looks like this. Yes, of course.
Actually, already about the slide. Can you explain what you mean by commuting on this B of h? Like, can you write down something?
Excellent. Exactly. Very good. So this is exactly what I will do. Yeah. So phi gives rise to a certain. So M now has a matrix unit system here. Let's say epsilon A prime. And this one has a matrix unit system epsilon XX prime, the canonical one, the usual one. So therefore you can define an operator on H just by picking up this corresponding coefficient of my map phi. So it will be phi applied to the matrix unit system epsilon A prime. Now I am in this space, and I slice down, applying this as a functional on the lec mx, I arrive at an operator. So this will be just by slicing down. Let me write it like that. But that will be an operator thing, B of h. Right? So yeah, it's a slice, if you wish, a left slice or right slice of this functional applied to this operator. So this is something that depends on the operator coefficient corresponding to x prime, A prime. That's something in B of h. Equivalently, what I'm having here, this UCP map, is the same requirement as the following. Now, if I form the operator matrix EX prime, A prime over all XX prime and A prime, this will be a non-negative matrix. It lives, of course, in the whole XA with coefficients in B of h. Over there, it will be a positive matrix, and if I slice down the unitality, I need to encode somehow. This is the positivity. The unitality is that if I apply partial trace on the, let me get this right, on the A system of this E, I will have the identity on X tensor to its B of H, with the identity on B of H. So these are certain operator coefficients arising from these UCP maps. Now, the commutation relation simply says that these entries of these matrices, one of them will be for Alice, the other one will be for Bob, obtained in a similar way. They have to commute with each other. So E, X prime, A prime have to commute with F, Y prime, B prime. For all choices of indices. So that's what I meant by.
Okay, I understand mathematically, but I mean, usually like the commuting operator framework arises where we say, okay, like if I have this Alice and Bob, right, then the actions, your actions should commute. One way I can enforce it is with tensor product, right? But then I have this more general way of enforcing it with the commutation requirement.
Right.
So I mean now this phi and psi that is like, I mean I should think of B of H as kind of this shared.
Yeah, it's the shared system. So this is the kind of, yeah, this will be the tensor product in the tensor framework.
Right. So and then Alice has some space with this MX, right? And she can also act on BH. And I somehow want to say that these actions on BH for Alice and Bob commute. Why does this, like, how does it look operationally? I mean, in the usual model, right? I said, okay, if Alice does something and then Bob does something, then that's the same as Bob doing this thing followed by Alice. Right?
Yeah. So this can be seen just by the fact that these two maps here, phi and psi, you do not have you do not obtain a difference which one is applied first in a sense, is multiplied first, right? So let's see the tensor form. The tensor form is just phi tensor psi. This operationally has a perfect sense because Alice is applying a channel phi, Bob is applying a channel psi.
Yeah, but that's not what we want because they're not both acting on the same age.
All right. let me use a different notation. If H is one-dimensional, dimension of H is equal to 1, then T is just a map from MA to MX, and similarly for C. It's a unital map, so if I take the pre-dual of the dual, it's quantum channel. And in that case, I can form, okay, pre-dual. This is a quantum channel from X, Y system to M, AB system. That has a perfect operational meaning, I think, right? Because each of them applies a certain channel, so there's like some local operations, right? Without any entanglement. And now, if you want to add entanglement, you want to do this thing here. But tensor product is not the right thing in general, right? You will need to have a dot product multiplication, operator multiplication, like we had in the classical case for the QC framework. If you are only for the Q framework, it's perfect. You just have different Hilbert spaces, H1 and H2. You take the tensor product, and then you slice down a certain functional on the system H1 tensored H2. Like we did in the classical case. In the classical case, we have, and then you apply to this. I'm sorry about the notation, which is kind of different, probably from, definitely from Gemma's. Yeah. Have a certain state C. Slice down, you obtain from an operator coefficient, you obtain a number, a scalar. Exactly the same thing is happening here, except that now this operation will be from, if you slice it down, it will be an operation from xy into AB. If you have the tensor framework, you will need to play with C, which is in the tensor product of these two Hilbert spaces. If not, it will be some state on the Hilbert space H, which is some infinite dimensional or whatever Hilbert space joint kind of system, shared.
You have three legs. Alice has her private space, C sub A, and her output private space is C sub X.
Yes.
Bob has C sub B. And so the three legs, C sub A, tensor H, tensor C sub B. Alice acts on two legs. The C sub A and the B of H piece, tensored with the identity on Bob's leg.
Okay, right, and these are the two maps that we want to commute, right?
Yes.
Okay, this is, and that corresponds to that.
That corresponds to the interest
Okay.
community.
All right, wonderful.
So this is what Vern is saying, I guess, right? I mean, for Alice's side, it will be just identity here. For Bob's side, the opposite way, but this will have commuting.
Yeah, so you
Commuting
require, right, that somehow phi tensor identity on y commutes with
Exactly. That is exactly what it is.
So
exactly.
It's just this was what I was.
Excellent. Good. Excellent.
Thank you.
That's what it is. Yes. All right. So this is then the QC class, and the Q is similarly defined with tensor using tensors. Right. Finite dimensional spaces. So we arrive at some class QC. We arrive at some class Q. We have the log. We have NS. So we have the whole setup, but now lifted as a quantum-to-quantum correlations. Now, these matrices can be called stochastic operator matrices because this slice property really kind of boils down to some kind of stochasticity, right? Now, what is the analog of synchronicity here? This is a next question that I want to see. So now, synchronicity, if you want to lift it to the quantum case, of course, you do not have coordinates, you do not have x's and a's at all. So you cannot talk about x being equal to y implies a equals to b because you have some preferred letters, classical letters there that are being sent. So yes. Go ahead. No. Go ahead.
Just this QQ. What does that correspond to? Like, is that like entanglement and local operation?
This corresponds to finite dimensional tensor entanglement. QC corresponds to infinite dimensional quantum commuting, if you wish, entanglement, if there is such a term.
In this QQ, like these phi psi maps, instead of acting on the same view of H, they act on one part of the tensor.
Correct, and then you can just put it by adding artificially the identity. You can think of it like in the classical case. Correct. Right. So what is the synchronicity here? The synchronicity will be given by sending the maximally entangled state in the first system to a maximally entangled state in the second system. So let me give some notation. J sub x will be the state. So let me get this right. I guess we need to normalize like that. You have the matrix unit x prime, and then the same ones here, I guess. Right, overall x and x prime in my set. So this is in some coordinate form. Let's say it's a maximally entangled state. So what you want, let's call it concurrency. So gamma is called concurrent if it preserves the maximally entangled states. So we claim that, I want to make the claim that this is a kind of natural condition that generalizes classical synchronicity to the quantum setting. Why? Well, if you take a look now at different setups that this can be applied, you see that you arrive at kind of the expected things if you play with this version of synchronicity in the quantum case. So that's one argument, but by no means saying that this is kind of probably the only way to talk about synchronicity in the quantum case. That's just a definition. I don't even call it synchronicity. That's just a definition. All right. So now moving to, I want to play the quantum graph isomorphism game. So this means that instead of just having gamma that goes in one way, in one direction, from this system to that system, I also want a gamma that can be reversed, as in the classical case we were saying. So this means that your correlation, which is just a quantum channel, no signaling quantum channel, has to be, of course, trace preserving is for quantum channel, but you want it to be unital because you want, when you take the dual, to also have a quantum channel. So that's a unital QNS correlation. And then one can define, therefore, analogs of bisynchronicity or biconcurrency, right? You want to preserve the vectors in both ways. It turns that it is enough to have just in one direction. So you arrive at something. So this in general we will call bicorrelations. You can define now different subclasses again in the same way. So what works nicely is if you play with if you have your stochastic operator matrices to be chosen to be bistochastic, because in that case you can invert them. You can both directions. So what is bistochasticity? Here I'm assuming that x is equal to a, equal to y, equal to b. I already assume that x is equal to a over there and defining concurrency. So the QC class will look like that. I need to have a version of a bistochastic matrix. Again, it will have some coordinates, right? And now you want to have both trace preservations, not trace preservation, but kind of slicing. So if I slice partially along x, I will get the identity on the A system, tensored with some kind of identity on some Hilbert space, and similarly for the other way around. If you take a look now, what's happening if this is classical? Classical means that if x is equal to x prime, if x is not equal to x prime and a is not equal to a prime, then these are all 0. 4. So in other words, the only thing that remains is x equals x prime, a equals a prime. What does it mean that it's bistochastic? It means just it's a magic square in the sense of Gemma and authors. So it just boils down to something like that. This is a family of POVMs now that along every row and every column they add up to 1. Not permutations. We know that not every magic square of that sort admits a dilation to a quantum permutation. This is a result of Gemma and co-authors. So yeah, it's kind of something else than the quantum permutations that were discussed previously by Mateusz, by Mike, and in the previous talk. Right, so working with these bistochastic, so let's call these bistochastic matrices, operator matrices. One can arrive at corresponding classes now, QC class, for example, Q class, and so on. So these are the ones that are kind of amenable to playing the quantum graph isomorphism game, which I will kind of define. I know that Laura will have an objection about using the term game, maybe. Let's say quantum graph isomorphisms without the game, because yeah, is it a game, is it not a game? Yes, so this, I hope we will decide that later, right, at some point. So, right, so first of all, again, as in the classical case, we want to have a tracial description of those, which is the encoding sister algebra here. And again, this links to the talks of Mike and of Mateusz about compact matrix compact quantum groups, right? So you want to start with, so what is the encoding algebra, the equivalent of the quantum permutation group here? This is what I want to describe now. So encoding sister algebra. So here you will start with a certain operator unitary. This is a certain operator unitary. And then what you want to do is you want to define, so this gives rise to a certain compact matrix compact quantum group, the sister algebra generated by all those. Right, so this was already given in the very first lecture on quantum groups. So the property that this is a unitary operator. And inside here, I will generate a smaller sister algebra, which I'm told by Mike, it is also a quantum group. He will chip in for sure here if that's not the case. Right, so I will define generators mimicking some kind of projection kind of, projective kind of. Very good, very good. Thank you very much. Thank you very much, Mike. So this will not be enough. Unitary will not be enough. Thanks. This will. I want it to be. This is unitary plus the transpose is also unitary. So this distinction was discussed in fair detail during Mike and Mateusz's talks. So I want to have something. Let's call it biunitary. So this U, capital U here, has the property that both U and U transpose are unitary matrices. So if you write down the relation, that boils down to certain algebraic relations. Now I will define associated with that the following factorized form. So I will have one of those generators and then another one like that. And I generate a sister algebra out of those inside this quantum group. So let me call it, yeah. Right, so C we haven't used. C, X, it really depends on X only here. Right. And the theorem is, well, the observation, if you wish, is that fact bisynchronous, or they will be biconcurrent here. So concurrent bicorrelations corresponds to traces on this sister algebra. So gamma from MXX to MXX is concurrent quantum commuting bicorrelation, precisely when it is given by a certain trace on this sister algebra. So there is this certain tracial state on C sub X. Such that if you take a look now at the coefficients or Chern matrix of this UCP map, this CP map, so gamma is given by, so this is in coordinate form. So you need to apply your trace at you have to have quite a lot of variables here, right? You have to have a lot of variables because you're acting from xx to xx, right? So you will have xx, xx, and one more time of those as coefficients, right? As Choi coefficients of the map. So therefore, you will have this generator of the sister algebra multiplied by, and it's tempting to say that it's the same with the y's. It turns out you need to swap these ones. And this swapping comes from the fact that the opposite, if you take a look at the opposite sister algebra of this, it is not, there is an isomorphism, right? There is an automorphism. There is an isomorphism between Cx and the opposite sister algebra, which will send the generator to the swap generator in the other sister algebra. So this is why the swapping takes place. So this is all a huge matrix over x, x prime, a prime, y prime, and bb prime. So what is lying behind this is the following factorization. So one of the ingredients here is the following. If you have, for example, just a stochastic operator matrix, so if E is a stochastic operator matrix, so E is just has some coefficients, x prime, a prime, then you have a factorization, pointwise factorization, entry-wise factorization of the following form. So your entry corresponding to x prime and a prime will be factorized as v a comma x start v a prime comma x prime, where v, which consists of these entries, is an isometry. So something kind of pretty is happening here. If look a little bit at that. When you have a stochastic matrix, this corresponds to channels from the first system into the other system into the second. So there's one-sided thing. They only can map from the first system to the second system. They cannot be reversed. In that case, you will need to encode them with isometries. If you now have bicorrelations, in other words, bistochastic, bistochastic key, you will have the same formula, but V will be required to be a biisometry. So V is a biisometry. And this means that both V and the transpose of V are isometries. Now, this is before you go to concurrency. If you go to concurrency, you're interested, for example, to characterize what's happening with the concurrent correlations. Then in that case, the operator that will appear here will be unitary. And if you want to go to the biconcurrent ones, it will be a biunitary. Right? They will be encoded by biunitaries. So I have this kind of 4 different versions represent. Yeah.
So in this theorem, do you want biconcurrent?
Yes, yes. It's only, yes. So this is automatic. Bicorrelation plus concurrent implies biconcurrent. Yep. Right, so how can we kind of use this as possible? So I will only mention this very briefly because I want to talk about something that I promised to Laura, about unitary basis, also how it can be placed in this setup. How do we play, for example, or try to arrive at some kind of operational quantum graph isomorphism? So you want to have, here is my first system, xx, here is my another system, also xx. I want to have some quantum graph in here. But quantum graphs, the way I define them, they were just operator systems in mx. And because in my game I want to have 2 inputs, I will vectorize this. So first of all, because I don't want to have loops, I better take the orthogonal complement of this, and then afterwards vectorize. So this was discussed by Gemma. So basically this space, this orthogonal complement of an operator system, it can be viewed as some subspace of C of x, Cx tensor with Cx, just by spreading the vectors around. I'm omitting here a little bit of detail of conjugate spaces. Let's forget about this. Let's say it's XX tensor XX CX, right? So you have a certain space here that is kind of a vectorized version of a quantum graph. You have a space, say, U sitting in here. Similarly, you have a space V sitting in here. So this will be V sitting in also the same thing. And now you can talk about the projection onto this space, P sub U, which will be just a projection in now XX. Here you have P sub V, a projection in XX. And now you can play this game. You have Alice and Bob. They are given states. They are given states that certain state, the two parts of a maybe entangled state that is supported on this quantum graph. They apply their strategy. They spit out something on the other side, and the referee checks against this projection whether they have won or lost. For them to win, the support of their output has to be contained in this projection. That in that case you will have perfect strategy. And now you can declare when you have perfect strategies, and then you notice that this I will not write down in detail. You have the generalization, a quantum version of the intertwining between adjacency matrices of classical graphs through a quantum permutation due to Laura and David and co-authors that I explained in the previous lecture. So this didn't mean to be, I didn't mean to have kind of a, yeah. Yeah, let's see, yeah. So it's something that we were working with Mike and Sam Harris and Ludmila, right? So that's what I wanted to say. It didn't mean to be a research talk. It's not a research talk because kind of naturally follows the flow from the previous talks, right? So here you have kind of an observation or theorem, a consequence that you have quantum isomorphism between these two graphs. So if you want, you can go to the operator systems that generate them even. They're all the same thing. I know that it is not the same for everybody what a quantum graph is, but for me it's just the simplest of all possible things, just an operator system, finite dimensionally acting operator system. It's the simplest possible thing. Precisely when, so this can be translated into an algebraic conditions on intertwining UU and P sub V with some sorts of bi-unitaries arising from the underlying bi-unitary that I started. Right, so I have 6 minutes, a little bit more. Just one little note now, how this fits into what's called super dense coding. So here, we just want to have now classical to quantum game. In this case, the outputs are classical, the inputs are classical, the outputs will be quantum. In this case, the encoding algebra will be the following one. So I will take the free product of some copies of the matrix algebra over A, x many copies. This is on Alice's side, similarly on Bob's side. So now, if you have corresponding concurrent strategy, it also arises from traces. On this algebra, let me call it B. Traces on B, it depends on X and A. So let me now consider the following game. So this will be a graph, classical graph, full complete graph on D squared vertices into a quantum full graph on D vertices. A quantum full graph on D vertices is just the orthogonal complement. Let's call it Q sub D. This is the orthogonal complement of the D-dimensional maximally entangled state. So this is the quantum version of a complete graph. So if you try to play this game, what you will observe is that the perfect strategies, the quantum perfect quantum strategies, so it will be Q sub Q strategies, that have to be concurrent because I'm playing a graph homomorphism game after all, so it better be concurrent. So I insist on concurrency plus perfection for this game. So perfection for this game means something like that, right? If I'm given here to different vertices, the output has to be orthogonal to the maximally entangled state on the other side. That's the only condition. It turns out that this arises from unitary basis. Of MD. Perfect quantum strategies, and I will say on CD. Only on this space. D dimensions. So they arise from unitary basis on MD, and unitary basis is just a kind of bunch of unitary operators. So for every A and B in D, it's a unitary operator such that they are orthogonal to each other in the trace in the product. That's kind of not difficult to see here, right? That you can have, every time you have such a basis, you will have a representation of BXA into MD, and vice versa. If you have a representation in here, you can arrive at a unitary basis. But these representations, finite dimensional representations, through the theorems, respective theorems for the classical to quantum case, they correspond to quantum strategies. So quantum correlations of quantum type that are classical to quantum correlations. Somewhere in between. We had classical to classical in the beginning. Afterwards, I talk about quantum to quantum. These are classical to quantum. So that's quite easy how to observe. And then finally, therefore, we have translated this graph homomorphism game between complete graphs into the existence of some unitary basis. And now, finally, unitary basis, they are linked to superdescoding and teleportation. There is a nice paper of Werner, Reich and Werner. That's a relatively probably old paper, and basically it is entitled, I think, All Teleportation Schemes. And over there, he's establishing this very nice equivalence between all these things, between superdense coding, teleportation, and unitary basis, right? And that is done only in the tight case, which means that your representations here are in MD. Open question, so Robin wanted open questions. What's happening if you allow not tight homomorphisms that have representations into higher than D dimensions? We do not have this correspondence anymore. So in the last 1 minute and 20 seconds, how do you build superdense coding scheme from a bunch of unitaries that form a basis in MD? So in superdense coding, what your aim is, Alice wants to send a certain classical message, so she's given, here is Alice, and here is Bob. So Alice is given a certain message X. They share a certain entangled state, omega. Alice has a choice of quantum channels to apply on her part of the entangled state. So she has piece of X, where X is in the message kind of pool. This is a quantum channel that she, given the message X, she wants to apply it to her part of the state. So Bob receives something. He wants to measure his part of the state with respect to some measurement that he has. Let's call it F sub y. And what you want is that this is Kronecker delta of xy. if you are given a unitary basis, you can build up dx and f sub y in the following way, and this is where I will finish. I'm aware that I have minus 10 seconds, so this will be minus 20 seconds, I promise. Starting with your unitary basis, you can start with a maximally entangled vector, capital omega, and then you apply unitary tensor 1 to omega. This will be certain vector cx. My f sub x will be the corresponding rank 1 operator arising from this xi, and my channel tx, or Alice's channel tx, will be just a conjugation, rho will be just a conjugation by this unitary. So this is how you can go from one to another. They're kind of equivalent in the tight case. All right, so that's it. Thank you.
So Delaware has this notion of, a CP map on Mn factoring through 2, 1. Is your gamma, is that the same as her idea of factoring through, but it's not just a 2, 1, it's factoring through a representation of
Right.
UN plus?
Mm-hmm. Yeah, eventually, a posteriori, after the characterization, it arises exactly in that way. But you have two left systems, bipartite. Instead of just mk, you have mk squared.
Thank
Thank you very much. Thank you.